Turbo machine, centrifugal pump. For today, we would like to discuss again about the blade type in centrifugal pump. As we mentioned in previous video, we have three blade type. One is forward, radial, and the backward. This is the forward blade, and it's something like this, and we could draw the velocity triangle as this one. I have explained detail about this in my previous video. So this is the velocity triangle at inlet, and this is velocity triangle at outlet. And the forward blade has blade angle more than 90 degrees. This is radial. Bear in mind that the radial is actually reflect the blade shape at the outlet, so not the inlet, at the outlet. So the outlet is radial, is straightforward, 90 degrees like this, parallel with the radial direction here, so we call this a radial blade. And the velocity triangle at the outlet will become like this, and we assume that VR2 is equal to VF2, and here U2 is equal to VWall2. And this is the backward blade like this, and then the velocity triangle is like this, and the blade angle is less than 90 degree. So you may refer my previous video about how to draw a velocity triangle in blade. And then we need to know the effect of blade type. Centrifugal pumps do not always have backward curved vane, but when they do, it is mostly for fluid in the incompressible regime of operation, such as water. For compressible operation of fluids, such as an air, forward curved vane centrifugal pumps are used. The net ideal head developed by a centrifugal pump is given by H ideal is equal A minus BQ, where A here and B here is the constant for a given impeller running at a given speed, and Q here is the volume flow rate at the impeller outlet. So sometimes when you buy a pump, the manufacturer will give you this equation. They will give you what is the value of A and what is the value of B to represent what is the H ideal, the pump head, the ideal pump head for that centrifugal pump. So why the blade type is important? Because blade angle will give you this kind of curve. For example, if we have curve of ideal head and discharge, we found that if we use backward facing, if we increase the discharge here, the ideal head mean the capability of that pump to transfer water from low to high level will decrease. And then if we have a radial, it's not significantly changed, but for forward blade, we found that if we increase the discharge, the flow rate inside the pump, the ideal head can be increased. Do note that the value of the actual head developed by the pump will be lower than this ideal value owing to shock. Means that the theoretical head and the actual head will be different. For sure, actual head will be lower compared to the theoretical head because there is a resistance or there is a losses. So the idea of losses, we call it H of shock is equal to K1 times QD minus Q square. QD here is the theoretical volume flow rate, and Q here is the actual volume flow rate, and K1 here is the resistance coefficient. So, and then we could simplify that shock here is actually friction, so we could write as head of friction is equal to K2Q square. So K2 here is the value, so the value of friction coefficient. So in Fluid Mechanics 1 and Fluid Mechanics 2, we are focusing to have value in F L over D V square over 2G, but in option subject in hydraulic machine and pipe system, we will learn about how to calculate the losses by using K2Q square here. This is the graph showing the actual head and the discharge, and then this is the curve shown by the backward blade, and this is the radial and this is the forward. So and then we could say that in reality, so the actual head here will have this kind of curve, and we found that when the pump has backward blade, so if we increase the discharge, so the actual head will decrease, and the radial it will slightly increase, and then it will decrease like this, and the forward will give a long range of increment in actual head before it's going down like this. So the idea of having this curve is when you operate centrifugal pump, you must know that every time you increase your discharge or your volume flow rate inside your pipe, it doesn't mean that you could create high actual head. So means that you must know what is the balance, what is the best discharge of flow rate for that particular centrifugal pump to have your optimum or your best manometric head here. And then the power required to drive the pump to provide a given flow rate is given as P is equal to rho GQH, where H is the head of ideal for certain pump, and the representative curve are given below. So if we have a power here, and then you have a discharge here, you will find that the backward will curve like this, the radial is something like linear line here, and the forward will increase like this. So it means that if we increase the discharge here, so for the backward here, the power is slightly not give so much a difference, but for radial, you increase the discharge, the power required to operate that pump will increase too. And also the forward blade centrifugal pump, if you increase the discharge inside that pump, so the power required to operate the forward blade centrifugal pump will exponentially increase. So it means that for backward it might be not too much different here, but for radial and forward you will need more power to have more discharge here. But if you see the relationship between discharge and head here, you will find that if you increase discharge, sometime the manometric head or the head of pump will not increase. So means that it is just you have no it is just no need to increase the discharge because it just only increase the power required. As is evident from the power discharge characteristic of the radial and forward vane centrifugal pump, the power requirement increase monotonically with an increase in discharge. Hence, if the pump motor is rated for maximum power, then it will remain underutilized for most of the operating time and result in an increased cost due to its higher rating. On the other hand, if a motor is rated at the design point and due to some reason the flow rate exceeds the design flow rate, then the power requirement will shoot up in case of forward and radial vanes only, causing overloading and motor failure. However, for backward curved vane centrifugal pumps, if the flow rate exceeds the design flow rate, occurs quite close to the maximum of the power discharge curve, then, contrary to the earlier case, the power requirement drops down as evident from the curve. This enables the motor, which is rated at the design power, to handle the entire range of flow rates without any problems. The actual design point is located correspondingly to the flow rate at which maximum efficiency occurs. And this table shows the comparison of blade type and its usage between these three type of blade. So we have backward, we have radial, we have forward, and this is the velocity triangle at outlet. So we already have another session talking about velocity triangle, but the velocity triangle at the inlet here, as you could see, so I simplified the velocity triangle into this one. So means that I simplified the value of V1 here is equal to 0, and it will make V1 is equal to VF1. Also in radial, so V1 and VF1 will occur like this, and this is V1 equal VF1. So I will explain why we could assume V1 equal to 0 in my next video. So for backward here, it is for low volume, and then it could be operated at high speed, and it is stable, and it shows excellent efficiency, and it is suitable for liquid. However, for radial here, it shows it is for intermediate volume, and because the speed is also intermediate and the stability is also intermediate, it shows low efficiency for liquid. It's easy to build, it is low cost, and it is suitable for a small pump. And this is for the forward. It could be used for the high volume, but it must be operated in low speed. It is not suitable for liquid. It shows low efficiency for liquid, and it is suitable for gas. So I hope by having this table, you could explain the advantage and the disadvantage of each type of centrifugal pump. The disadvantage here, it means that we need to choose a suitable pump for a suitable application.